Hi there, so this video is on the second part of section 2.3 on higher order derivatives. And higher order derivatives are just when we're thinking about taking the derivative of a derivative. So like if you take the derivative of the first derivative, we refer to that as the second derivative. And the derivative of the second derivative would be the third derivative, and so on. But really this set of notes is going to focus in on an application of higher order derivatives, which is thinking about a moving object or starting with a function that represents the position of an object. Okay, and the first derivative we've talked about of a position function, so s prime, if s of t represents a position function, then s prime of t represents the velocity function. So s prime of t is equal to v of t, we could say, if you wanted to rename the function with v. Now the derivative of a velocity function, which would be the second derivative of a position function, is acceleration. So acceleration is also a vector quantity, just like velocity. So it has both magnitude and direction. And acceleration is the rate at which velocity is changing. And that should make sense, right? Since it's the derivative of velocity, an acceleration function would give us the rate of change of velocity. And since velocity is speed and direction, there's only two ways for an object to accelerate. So either there's a change in speed, or there's a change in direction, or both are changing. So the magnitude of acceleration, that value tells us how much the speed of an object has changed. And then we, in our exploration last class, determined what it means, or how you could justify that an object is speeding up versus slowing down. And what we concluded was that if acceleration has the same sign as velocity, then the object will be speeding up. And that could be talking about at a particular moment in time, or it could be over an interval of time. But that would be the justification. So if acceleration and velocity have the same sign, that means the object is speeding up. And then if the object would be considered to be slowing down if acceleration has the opposite sign as velocity. So if acceleration is positive and then velocity is negative, then that would mean that the object would be slowing down. Okay, so this graph is a velocity graph. It represents the velocity of a particle that's moving along the x-axis. So if we're thinking about a particle moving along the x-axis, that means that the particle is either moving to the left or the right. And for these linear motion problems, it's going to be one direction or the other. So it would be common for, depending on what information is given about the movement, to be moving left or right, forwards or backwards might be the terminology used, or it could be up or down. So in this case, we are thinking about the particle moving along the x-axis, which indicates moving to the left or the right. Okay, so going through this, it might be fun to pause the video here and see if you can answer the questions A through E, and maybe even that last question here, at what times does the particle change direction? So you could pause right now, and then you could check your answers because I'm about to go through them. Okay, so notice that the question here, or the directions say to find the open intervals on which the particle is doing these different things. So all of my answers are going to be open intervals, so using parentheses, not including any of the endpoints. You want to make sure that you're looking at the wording of the question, because for some of these, if it wasn't specified to find an open interval, you could end up with like a half open interval, or even potentially for a different problem, a closed interval. So for where the particle is moving to the right, the particle would be moving to the right when velocity is positive. So looking at this graph, which is defined just from 0 to 7, there's no arrow at the end of the 7. So it's just from 0 to 7. we can see that velocity, here, let me pick a different color here, would be positive. It looks like from 0 to 1. And then velocity is equal to 0 at 1. So we can't include 1 for when the particle would be moving to the right. But then it's also positive. It looks like from 1 to 4. And then from 6 to 7, okay? And we can see the x-intercepts, or sorry, the t-intercepts, where the velocity graph intersects the horizontal axis, would actually correspond to where the velocity would be equal to 0. So if velocity is going to have a sign change, it would occur whenever v of t is equal to 0. So if there's going to be a change in direction, that's where it would happen. Okay, so listing these intervals, the particle would be moving to the right first on the interval from 0 to 1, and then from 1 to 4, and then from 6 to 7. And if you were justifying, you could say, like, because v of t is greater than 0 on these intervals. So where the velocity is positive, that means that the x values, right, the particle is moving along the x-axis. So as time is passing, the x values would be increasing. So velocity, that means velocity would be positive. Okay, so for moving to the left, that would be wherever velocity is negative, and it looks like that would be on the interval from 4 to 6, right? Because that would be whenever the x values would be getting smaller. So that would be velocity would be negative. So that's the interval. Let me write that down, from 4 to 6. Okay. And then C says where the particle is speeding up. Okay, well, if we go back up to our summary up here, remember an object would be speeding up, or in this case, the particle would be speeding up whenever acceleration has the same sign as velocity. Okay, well, since acceleration is the derivative of velocity, we could think about the slopes of the tangent lines for velocity to determine what the sign of acceleration is, right? Like, so wherever there's positive sloping tangent lines on this velocity graph would correspond to acceleration being positive, and wherever there's negative sloping tangent lines on the graph of velocity, that would be where acceleration is negative. So it looks like, where does it look like velocity and acceleration would be the same sign? So on this first interval from 0 to 1, velocity would be positive, but it actually looks like acceleration would be negative on that interval because velocity is, well, decreasing, right? Negative sloping tangent lines would mean velocity is decreasing on that interval. Okay, so then we keep going. It looks like from 1 to 2, velocity would be positive. And it also looks like velocity is increasing. So positive sloping tangent lines means acceleration would also be positive. So that would be our first interval for where the particle would be speeding up. So from 1 to 2, because velocity and acceleration would both be positive on that interval. Okay, and then from 2 to 3, velocity is positive, but acceleration would actually be 0, right? The slopes of the tangent lines on that interval would be 0. Okay, so then from 3 to 4, we look, velocity would be positive, but acceleration would be negative because velocity is decreasing on that interval. Okay, so then we move to from 4 to 5, the interval from 4 to 5. So velocity would be negative, and it actually looks like velocity is decreasing on that interval. So negative sloping tangent lines, which means acceleration would be negative. So we could say from 4 to 5, the particle speed would be increasing, or the particle would be speeding up. And then from 5 to 6, velocity is negative, but looks like velocity would be increasing, so acceleration would actually be positive on that interval. And then from 6 to 7, velocity is positive and increasing, so that means acceleration would be positive. So velocity and acceleration would both be positive, and therefore the particle would be speeding up on the interval from 6 to 7. Okay, D, we kind of answered this as we were trying to answer C. Here, let's choose a different color here. So there would be positive acceleration. So that would be wherever it looks like velocity is increasing for there to be positive sloping tangent lines. So that looks like it would be the interval from 1 to 2, and then from 5 to 7. Looks like that would be where there would be positive acceleration. So from 1 to 2, and then 5 to 7. Okay, and then for where the particle would be moving at a constant speed. For where the particle would be moving at a constant speed. So remember that speed is the magnitude of velocity. And so looking at this graph, it looks like the only place that velocity would be constant would be from 1 to 3. The velocity, the outputs for velocity are not changing on that interval. So we could say from 1 to 3, the particle would be moving at a constant speed. Okay. Before we move on to at what times the particle changes direction, I do want to point out that if this hadn't been stated, so if we hadn't been explicitly asked for open intervals, at t equals to 0, velocity is positive. So we would want to have included 0 in that case. And then same thing at t equals to 7, velocity would have been positive at that endpoint, and we would have wanted to include 7. But again, you want to make sure you're reading the directions, and the directions did say find the open intervals. Okay. So for where the particle, or at what times the particle changes direction, so when it changes from left to right or right to left, we could kind of put it together like looking at part A and part B. But for the particle to change direction, it would have to have a velocity. For velocity to change sign, it would have to pass through 0. So like at t equals to 1, while the velocity is 0 at t equals to 1, the sign of velocity does not change. But at t equals to 4, and then at t equals to 6, there is a sign change for velocity. So we're looking first at where v of t would be equal to 0, so where the velocity would be equal to 0, because the velocity would have to be passed through 0 for there to be a change in direction. So for where v of t is equal to 0, that ends up being at t equals to 4 and t equals to 6. Okay, and then if we were being asked to justify, which this is a really like common type of question that you would be asked to justify, you would have made that statement about like those are the values where v of t is equal to 0, and then you could say something like the particle changes, I can't write right now, changes direction at t equals to 4 and t equals to 6 because like v of t changes, you want to be specific, changes from positive to negative at t equals to 4, and v of t changes from negative to positive at t equals to 6. Okay, so that would be our justification. You do want to be specific. You want to say, like, the function that we're seeing the graph for, v of t, changes from positive to negative at this value. V of t changes from negative to positive at this value. You can reference past. We will get really into looking at past free response questions, but there was actually a question that required this type of justification on last year's exam. It was number 2A. If you wanted to go on College Board and check it out, we'll look at it eventually in class. But from the 2023 exam, number 2A required a justification like this. Okay, so let's look at another particle motion. It's just a linear motion type problem, but this is talking about a particle moving. So it says a particle moves along a horizontal line. Okay, so if we think about there being a horizontal line, and then the particle would have a starting position at t equals to 0, and moving along a horizontal line, it's either going to move, that particle will either move to the right or it'll move to the left. Okay, so its position at any time t greater than or equal to 0 is given by the function x of t equals to t squared minus 4t plus 3, where x is measured in, measured in feet. Okay, so that would be x of t would be position in feet. Okay, and t is time measured in seconds. Okay, so t is time measured in seconds. So our first question here is asking us to find the displacement of the particle during the first 3 seconds. So displacement can be described as a net change in position. Okay, it is also a vector quantity, which describes the distance and direction from start to finish. So with relation to where you start, like how far is it to where you finish, or in this case, the particle, like what's the distance between where it started and where it finishes, and as well as the direction. Right? You need magnitude and direction to describe a vector quantity. Okay, so to calculate the displacement, the distance, we could just look at, so first 3 seconds, that would be the interval from 0 to 3. So we could look at x of 3 minus x of 0. So x of 3 minus x of 0. X of 3, it looks like, would be, 0, right? 3 squared would be 9. Minus 12, yep, would be 0. And then minus x of 0 would be 3. So we end up with displacement being negative 3 feet. But what does that mean? What does that negative mean? It means that during the first 3 seconds, the particle is displaced 3 feet to the left of its starting position. Okay, so we have given a magnitude as well as a direction to describe the displacement. Okay, find the average velocity. The average velocity of the particle during the first 3 seconds. You guys know how to calculate average velocity. So average velocity, think slope formula. Average velocity over those first 3 seconds would be change in position, displacement, divided by change in time. So 3 minus 0. So, and that would, we've already calculated displacement, -3 divided by 3. So we get -1. Okay. And the units would be feet per second. An easy way to check that is like the units for displacement or that change in position would be feet. And then over time is being measured in seconds, so feet per second. Okay, so we can interpret that negative as direction. And there are a couple different ways that you could write this out. So one way, here I'll write it in 2 different ways just to show you. So the first way, and it's saying explain its meaning. We could say during the first 3 seconds, the particle averaged 1 foot per second moving to the left. Right, that negative indicated to the left. Or the other way that you could write it is saying something like during the first 3 seconds, the particle on average moved left 1 foot each second. Okay, one tells us a little bit more about position. One gives us more like direction and speed. The first one gave us the speed and then the direction, right? Magnitude of velocity is speed. So speed and direction. And the other one kind of gave us a description about position, like in terms of position. Both would work. You just want to make sure that you're answering appropriately if it asks you to answer like in terms of speed and direction, if there's like very specific directions. Okay, so find the particle's initial velocity and its velocity at t equals to 3 seconds. Well, it's just saying velocity. So that indicates, it doesn't say average velocity, so that indicates instantaneous velocity. Initial velocity would be whenever t is equal to 0, and then we have at t equals to 3 seconds. Right, so when t is equal to 0 and t equals to 3 seconds. We need to figure out what our velocity formula is. So we have our position function, and to find our velocity function, we just have to think about taking the derivative of our position function. So x prime of t, which I can rename v of t, thinking power rule would just be 2t minus 4. So x prime of 0, which would be the same as v of 0 if you wanted to rename it, would be -4 feet per second. And then x prime of 3 would end up being +2 feet per second. Okay, and it says explain the meaning of each in terms of the particle's movement. Okay, so in terms of the particle's movement. So to do that, I would say, something like at t equals to 0 seconds, the particle is moving at t equals to 0, our velocity was negative, so is moving left at 4 feet per second. Okay, so we get the speed and the direction, magnitude and direction. And then at t equals to 3 seconds, the particle is moving right at 2 feet per second. Okay, so again, giving direction and magnitude. Okay, I knew it was moving to the right at t equals to 3 seconds since velocity was positive at that time. Okay, so now we're asked a question about acceleration. Okay, so we want to find the acceleration of the particle at t equals to 3 seconds and explain its meaning in terms of the particle's velocity. Okay, so first of all, we need the second derivative of our position function, which would be the first derivative of our velocity function, which you could also rename at this point as a of t. Okay, and the derivative of our velocity function would just be 2. It would be a constant. So that means that a of 3 would be 2. Now, what would the units be? Okay, well, if v of t is equal to x prime of t, another notation, remember, for x prime of t, which is the derivative of that position function, where it was position in feet as a function of time. So its derivative could also be written as dx over dt, where x is measured in feet, time is measured in seconds. Okay, so that's a nice notation for determining units. Well, since a of t is the derivative of velocity, that could be written as dv over dt. Velocity is measured in feet per second, and time is still measured in seconds. Well, feet per second, that's one way you could write it, or that can simplify down to be feet per second squared. Okay, so where we could say at t equals to 3 seconds, the velocity, and it's asking us to answer in terms of the particle's velocity. So we would say the velocity is increasing, because we got a positive value, by 2, you could say by 2 feet per second, or you could even write, you can write one of these, either per, every, or each, choose one of them, second. In order to, because we weren't just asked for the acceleration, we found the acceleration, but we were asked to answer in terms of the particle's velocity. So velocity is increasing at a rate of 2 feet per second. Okay, so at t equals to 3 seconds, is the speed of the particle increasing or decreasing? Justify. Okay, well, that means we need to figure out what the sign of velocity and acceleration are at 3 seconds. We already figured out acceleration at 3 seconds. Did we already figure out velocity too? Let's see. Oh, we did. We got to summarize. We got that velocity at 3 seconds was 2 feet per second. and we got the acceleration at 3 seconds was also positive 2 feet per second squared. So both are positive, right? Both of these values are greater than 0. So speed is increasing. So the way that we would justify, or we would summarize and justify our answer, is we would say the speed of the particle is increasing at t equals to 3 seconds because the particle's velocity and acceleration are both positive at that time. They would probably even take that they're the same sign. I referenced, for making sure that I was answering that question appropriately, I checked our 2023 exam, so last year's exam 2B, had a justification that was similar. Okay, so during what times is the particle moving to the right, to the left, and at what values of t does the particle change direction? Okay, well, change of direction means that velocity would have to change sign, so it would have to pass through 0. So why don't we first think about where velocity would be equal to 0. So velocity is 2t minus 4, so setting velocity equal to 0. And solving that equation, we would end up with t is equal to 2. So velocity is 0 at 2 seconds. And we were also, for this problem, given our domain is that t is greater than or equal to 0. Okay, so I'm going to make kind of an analysis line here. 0 is an endpoint, and then when t is equal to 2, that's a potential sign change for velocity. So I want to figure out what direction the particle is moving between 0 and 2, and then to the right of 2. So thinking about using test values, like if we were to plug in 1 as a test value into, we want to see what velocity would be. So we're thinking like v of 1. V of 1 would be -2. So it would be negative. Okay, and then v of 3 would be positive. Okay, so that means that the particle between 0 and 2, when t is between 0 and 2, the particle would be moving to the left. And then whenever, for t greater than 2, the particle would be moving to the right. Now let's check, since we are given this domain, if we were to find v of 0, so the initial velocity here, v of 0 would be -4. So velocity is actually negative at 0. So we're actually going to use a half open interval here in order to describe whenever the particle is moving to the left, right? So to the left would be whenever v of t is negative. To the right would be when v of t is positive. So we could say something like the particle moves to the right for t strictly greater than 2 seconds, since v of t is greater than 0 on this interval. Okay, and then we can say the particle moves to the left for t greater than or equal to 0 and less than 2. Since v of t, our justification, since v of t is less than 0 on this interval. And for the change of direction, we would want to say something like the particle changes direction at t equals to 2 seconds because v of t, or since v of t is equal to 0 and v of t changes from negative, changes signs, right? But we want to be specific, changes from negative to positive at this time, or at t equals to 2 seconds. You want to be specific. Okay, so answering for when the particle is moving to the right, to the left, and when it changes directions. Change in direction is whenever velocity changes sign. Okay, and then for find the total distance the particle travels during the first 3 seconds. I think I'm actually going to leave this so we can check in as a warm-up next class. So why don't you think about this one? Find the total distance that the particle travels during the first 3 seconds. Okay, so we will check in with each other on this question.